Before the break, I left you with this question. If we consider KCI attacks, so I corrupt the party, and then I can impersonate to that party. This is not covered in the BR security game, the secrecy game. Can you tell me why this is the case? Anyone besides Yehuda who? Say it again? Exactly. Basically, we don't care about secrecy of keys of corrupt parties. Right. So this was the definition. And you see down here it says the tested party or the party in the test session nor its partner is corrupt. Now, in KCI attacks do exactly this, right? They corrupt the party and then they are able to learn the session key. But we don't care about this. So this is why it's not included in the BR model. Okay, and as I've said, TLS 1.3 still looks good. Right, even though if you give a security proof in the BR model, this may not cover KCI attacks. Again, if you have the client's key, you would still need to forge signatures under the server's key. Okay, so now the final slides of this part are about advanced models, and especially attacks on the state of the parties. So we've had this before. I told you that I work in the weak corruption model, so I can corrupt a party and then I get the secret key, the long-term secret key, but not the inner state, not the randomness which is used and so on. So the question is, can we do something about this, or do we have models that capture these cases? And there are two more or less distinctions, two cases to distinguish. One is I get the ephemeral key. Of course, this needs to require to define what an ephemeral key is. Typically, you would think like in TLS, it's a G to the X, so it's dx. Or you get the complete state, like including the randomness. And this is pretty clear from theory of multi-party computation. It means you get the full access to all the inner values party has. So there are models to capture these. One is the CK model, or as Hugo always refers to it as the SK model. I think Lamacchia, Lauter, and Mitjagan later called it CK instead of SK. And in this model, you can do session state reveals. With one exception, you cannot do it in a test session. Right? That's part of the model. And if you want to do it formally, you just add another oracle here saying, okay, I can push the button and then I get the session state as return. And of course, then restrictions. You cannot ask for the identity which is used in the test case here. So you would expect that this is stronger, maybe this is stronger, and all implies BR. And then there's a paper by Cascremas saying, well, not really. There are all these technical issues about when to choose session identifiers and so on. So there may not even be a strong hierarchy about this. But if you, as a rule of thumb, you can think of this is the strongest version of the BR model, and then it goes down all the way down to BR. Okay, and there's a famous, yeah.
I understand why you said you can't corrupt a long-term key in a session and an ephemeral key in any session.
Yeah.
But that's not the session of testing, so what difference does it make if I have nothing left?
No, in the test session. So in the test session, you cannot corrupt and make a state reveal, because then you have, you cannot.
No, but the ephemeral I can't either, even just the ephemeral I can't.
No, the ephemeral you can, right? As long as you don't have access to the long-term key, you should, as the honest user, should still be protected. If you miss one part of the secrets, long-term or ephemeral, you should still be good. Okay, so one of the famous protocols, I'm not going to talk about this, is the Naxos protocol, which achieves this eCK security. Now, if you talk about TLS 1.3, it's pretty easy to see that this does not achieve eCK security, and the reason is that if I have your ephemeral secret, which is the X here, right? If I have access to that, I can compute all the keys from there on. TLS does not aim at session state reveals, or it cannot provide security against such attacks. Except for pre-shared key. Yeah, with pre-shared keys, this may still be different. Talking about Diffie-Hellman version here. Yeah, pre-shared with Diffie-Hellman is different, right? Because then you mix ephemeral secrets and long-term secrets together. This is doable. Okay, and while I'm at this slide, I should also mention I got some questions in the break about more or less this notation here. There was some confusion. So this means I'm going to sign. This is the message part. I'm going to sign this message under this signing key. Okay, that's what this notation means. It doesn't mean I'm going to sign my signing key. I don't know, maybe other people use the notation SIG and then the signing key is down here and then you compute the message here. Maybe this is the other notation. And something else I wanted to mention is, of course, you don't just send a signature. The signature here is verified. No, actually, this is an interesting point because as cryptographers, we all essentially always ignore these verification things, right? We don't write explicitly, oh, you have to verify the signature, because this is quite natural to us. We don't write, oh, you have to verify that the incoming message is of a certain length and so on. And once you do this, and an engineer looks at this protocol specification or like this description and implements it, you shouldn't be surprised if the engineer, forgets the verification thing here, because it's simply not written there. Okay? Can happen. Think of Heartbleed, right? Suddenly I get a request to give me a long message as output. And yeah, of course, I don't check for length. Okay. But again, cryptographers, it's very common. You see in the rest of my talk and in the beginning of my talk, I ignore these verification things. Remember, they are there. Okay? Okay, so now we've seen, you have a basic understanding of the BR model. You know its limitations. You know how TLS fits in there and some other protocols and so on. So what if I give you this protocol? Okay, the protocol is the server has a certified public key. We're talking about unilateral authentication, right? Only the server authenticates. The server sends its public key and the nonce. The client picks the session key and encrypts it with the nonce under the server's public key and sends it back. The server decrypts and checks that what it gets here actually matches the value it has sent before. Is this BR secure? By now you should be able to make a wild guess. Yes, why? You have some intuition why? Exactly. If you think it closer to the model, Ooh, written a lot. There we are. Right, if you think about the protocol and you want to test the server session, the client is not authenticated. So basically you can only test the server session if it has been produced by some honest client, right? So let's forget about this case and just immediately talk about testing the client. So if I'm the adversary, and let's say I either pick my own nonce or I copy it from some other execution, and then I get to see ciphertext. In order to break the security, the BR security of that scheme, I would somehow need to be able to recover information about the key from the ciphertext. Now, I don't hold the secret key of the server, cannot be corrupt, otherwise the client has a corrupt partner. So my only chance, basically, is to somehow take the ciphertext and resend it in some other session to the server. And hope that this server then decrypts, says, hey, great, I got the key, and then I'm going to make a reveal. Now the problem is, if I send this ciphertext from this session here into that session, then the server will decrypt, recover the nonce which is sent here, right? And then check, no, this doesn't match my nonce, so I'm going to output error and stop here. So I'm not going to output the session key, and you cannot, as an adversary, you cannot reveal that. Right, and decrypting these false ciphertexts is fine, because if you assume that the encryption scheme is CCA secure, fine, I can do that. So basically, I don't have any chance to really learn something about the key. So great. Why use Diffie-Hellman and TLS and 4 rounds or 3 rounds, whatever? Just use that protocol. So why don't we do this? There's no really CCA secure public key. What about RSA OAP? What's that? Leichenbach. No, not on OAP, right?
No, with measures that the 0 byte, like most programmers will just build the sidechain and include the embedding OAP.
Okay. So I really hope that we have a CCA secure encryption scheme, and I'm positive that we have some good candidates for that, right? Everything's unproven. Yeah, that's not the reason. We're unprotected from man in the middle. Why?
Because somebody sitting this week can generate its own key and use it as it.
How would you sit in the middle? You would. You're trying to attack the client or the server?
The session.
The client session or the server session?
The client.
The client, of course. Okay. Okay, you're sitting here, and you want to attack the client. How? So you get this, and then?
I terminate this one.
Okay.
Generate a new one for the client.
Okay, completely new.
With my nonce.
And under your key or the server's key? My key. So this is Eve, right? This is an E. Okay, so then you get a ciphertext. Encrypted under E. Fine, you can probably decrypt this, right? Because you have the secret key of Eve. And then recover the key and the nonce. Okay. Is that an attack? It's a client who says, oh, okay, I'm talking to the malicious Amazon. And malicious Amazon knows my key. Because it's Eve's key, right? Think of this in terms of being a cryptographer. You're not going to try to protect this key in this session, right? Because it's sent to a malicious party, to a corrupt party, under its key. Of course, the corrupt party knows the key. So this wouldn't be an attack. Now it is really BR secure. Still, Ah, thank you. I was about, okay, can you just look at the title? It doesn't have forward secrecy. So forward secrecy, as Hugo said yesterday, is to protect keys from the past. Okay, so we've done that. So forward secrecy in this context means that if I later break your encryption scheme, in the sense that I recover the secret key, the long-term secret key, think about in terms of corrupt queries, then I can recover that session key, of course. Right? I'm just recording the communication. Now later I'm going to recover the key of the server, and then I can just decrypt under the server's key. Fine. So far we haven't talked about these attacks, right? We haven't protected against these attacks. Why? Because we say if the partner is corrupt, we don't care about secrecy of session keys. So as of now, we have excluded such attacks. Okay, still you want to have those, this security guarantee, and this is why we use Diffie-Hellman a lot in all these protocols. Because this would mean that, again, I'm recording the entire communication of the world, store it somewhere in my desert, and then 10 years from now, I'm going to use my quantum computer to break all the RSA keys. Then I can just go through my files and decrypt all the communication there, all the session keys, and once I have the session keys, I can actually decrypt the actual payload. That's quite easy, right? I mean, even if you think that running a quantum computer to break an RSA key may cost $1 million, for each user you do it just once, and you have all the communication of this user. Now this is why we want to have forward secrecy. So we still want to be able to protect if later a user gets corrupted, right? So 10 years from now, the quantum computer breaks RSA, but I still have some security guarantees of all these sessions till up to these 10 years. And we don't have to touch the model at all. We still have our corrupt, our send, and so on. The only thing we have to change is the freshness condition. So before we said, neither the party in the tested session nor the partner is corrupt. So now we're just going to relax this a bit, and we say, neither the party nor the intended partner is corrupt before the test session has completed. Meaning, I run the test session like this. This is my test session. I run it. Later I can make a corrupt. And this session would still be fresh. And for the other cases, unilateral, authenticated, and anonymous, you do the very same, saying, okay, if the partner is unauthenticated, so in the test session, in the same, then you say, but this party was only honest when the session completed. Later, it may have been corrupted. Yeah.
Don't we often get something a little bit stronger that even if it's later but it's not active?
Yeah.
After
Give me a couple of slides. I anticipated this question from you. You're so predictable. Sorry. Okay. Okay, so this is the interpretation, if you like. So in non-forward secret settings, what you have is if I corrupt a long-term secret, let's say of the server, then executions which happened before may be completely insecure, right? This is again the example where you send something encrypted. Then I get your decryption key and I can recover the session key. It may even be that sessions where it's not meant to be that the adversary runs the full session, but maybe it steps in halfway or modifies some messages, even where the adversary has been active in the communication, they are insecure. I don't have any security guarantees. And forward secrecy now tells you these sessions, the session keys, in such executions, good executions, executions between honest parties should still be secure. They should still be secure even if the adversary has been active. Right, here's passive adversary. This is meant to be an active adversary, up to the guarantees we can give. Right, if I intend to talk to a malicious party, I don't have any guarantee at all. But if the adversary just modifies some messages, I would still expect that my session key, if I derive it, is not recoverable. Okay, and again, the difference between the two settings and why we strive for forward secrecy is the following. Here it is enough to recover one long-term secret. Again, running the quantum computer once on the server side, I get all these sessions at once. Now in the forward secret case, it says if I corrupt this long-term secret of the server, these sessions are still good. Think in terms of these are Diffie-Hellman sessions, right? Plus some more, maybe some TLS. Of course, if I have the quantum computer, I can also go and compute discrete logarithms, right? But the difference is, I would have to do this once for this session, and then I can recover the session key one time for this session, Q for quantum computer, and one time for this session. Right, so I have to run the quantum computer 3 times. Think about the billions of TLS connections. I would have to run it billions of times to recover all the keys, and I can just attack one session. Question? What about TLS?
Why it makes a big difference if you need to apply Q more than once?
Ah,
After you need to read the messages, right? So you do make some effort.
yeah.
So if the quantum computer is strong enough, then you make some more effort.
Yeah, but again, I cannot protect you against breaking crypto, right? But I can make your life much harder if you have to, let's say breaking an RSA key is not like instantaneously, right? It takes, let's say, 3 months. Whatever. Maybe classically. Oh yeah, but it may be faster, I don't know. Let's say it takes 3 months, right? So here I have 3 months of workload, and then I can recover all the communication of this server over the past years.
If it takes 3 months, then I understand you.
Okay.
I think it would be like microseconds.
Well, the thing is, we're going to switch, right? I mean, maybe the...
Nobody thinks that. Even if a quantum computer is ever built, no one thinks it's going to be that. But forget quantum computers. Think about the NSA steals your long-term key. Is it enough for them to just do they get everything in the past, or is it not enough? That's realistic today.
Yeah, I didn't want to use that example. It's recorded. Okay, so let's look at TLS. Of course, it is forward secret, no doubt. And the reason is that if you look at the final channel key, right, then it is computed over an ephemeral Diffie-Hellman key exchange, this GX and this GY. If I later break your signature key, right, the long-term secret here is the signing key and the signing key on this side, if there is one on the client side or server side. If you break that, it doesn't help you to recover the channel key. It helps you to authenticate yourself in the next protocol execution, right? Because now you have the signing key, but forward secrecy doesn't give you any security in that regard. With a minor modification, okay? So even if you have later the signing key, this protocol run has already been completed. And this is the same if you, let's say, if you try to be, let's say you have a quantum computer and you can instantaneously break stuff, right? So in order to be able to recover the key, you would have to break, let's say break I mean recover the secret signing key of the server here. Then you can insert your own G to the Y star and then create a signature under the server's key, right? That's possible. But that's not what forward secrecy tries to protect. Forward secrecy tells you if the session is over and you corrupt something, then it's protected. This session, if I break it exactly at this point, is still running. And I don't have any security guarantees for running executions. Okay. So now there's a big part about two move protocols or two message protocols or one round protocols, depends on how you count. And the notion called weak forward secrecy, or as Hugo would like to say, weak perfect forward secrecy, I guess. Perfectly weak. Yeah, I'm going to make a comment once I'm there about this notion. Okay. So, and this is based, very often you read papers which say, okay, we're designing a cool, super cool protocol and it has two messages, right? One from the client, one back to the server, and that's it. And then they say, okay, there's this paper by Hugo saying, yeah, if you have a two-move protocol, you cannot have forward secrecy. Hugo doesn't say that. I have the quotation here. But it's kind of stuck in people's minds, I think. Okay, and what Hugo precisely says is, he talks about MQV, one of the protocols. It does not provide perfect forward secrecy. And again, perfect forward secrecy is always confusing for me, because I'm so used to perfect zero knowledge, statistical zero knowledge, computational zero knowledge. So I'm not sure what perfect here means.
Perfectly forward means that it's not.
It's okay, I can live with that. You didn't want to touch forward secrecy and you just added something to make it. Okay, I see that. Okay. Okay, and then he goes on, this, however, is not just a failure of MQV, but it's an inherent limitation of implicitly authenticated two-message protocols based on public key authentication, and which do not rely on the previously established state. Indeed, no such protocol can provide perfect forward secrecy. So you see there are all these caveats here, right? It's implicitly authenticated, it's public key authentication, seems to be the common approach, that's not the big deal, and there's no shared state. And the question is, in which security model at all? And I'm especially asking this question because you see that it really depends on what kind of reveals you have. Here we refer to session state reveals. Okay, so here's the attack on two move protocols. And now I'll talk about, okay, public key, fine, no state. Okay, let's accept this. And it's implicitly authenticated. And implicitly authenticated means, maybe I should first introduce the notation. So this is a general definition of a two-move protocol. Client has a long-term secret, a signing key, a decryption key, whatever. Of course, it has the certified public key and so on. Same on the server side. And for the session, the client picks some randomness, like a Diffie-Hellman value or whatever. Same on the server side. And then the client sends its first message. Typically, the message would contain like the public key and so on, but this is irrelevant. It's just one message going from left to right. And now implicitly authenticated says that the secret long-term key is not used here. So one thing you don't do is, for example, you create a Diffie-Hellman value and you sign it, because that would require your long-term secret to create the signature. Okay? And then the server computes its reply. This may carry a signature, we don't care. And then both parties can compute the key. Right? On the client side, now the long-term secret enters the computation, the randomness, of course, and the incoming messages. Right? If you have these two values, you can compute the outgoing message yourself, so basically you can also have it there. And on the server side, it's the same. It's the long-term key of the server, the randomness, and the incoming message. So here's the attack. The client just tries to impersonate, the adversary tries to impersonate the client. And how it does it is that it picks its own randomness and then computes the message as the client would. Now this is doable because this secret long-term key does not enter into that computation, right? There's no signature or something like this. I can just compute it from my own randomness and the public key. So then the server picks its own randomness, computes the key, and sends the answer. And now you attack this protocol. We're talking about forward secrecy, so the protocol, this protocol execution here is over. So now I can corrupt. And I'm going to do that. I'm going to corrupt the client. Corrupting the client means I get the long-term secret. And now what I can do is, I got my own randomness, I got the incoming message, I got the long-term secret. That's the same, or that's enough to compute the secret key. So I can just use these three values, derive the same key. If you think in terms of models, I can test this one, and of course I can easily distinguish it from random. Okay? And if you look closely, you actually don't even need this execution here, right? I can just mount the attack as is. Okay, so let's look at the general case. Right now, we may have explicit authentication. So for example, this message may contain now a signature over the signing key and some message. Right, and then I cannot mount the attack I've just shown you. But now what we do is, we give the adversary the state reveal. So now it can ask for the randomness, which is used to compute the answers. Okay, here's the attack. The first message may now carry a signature, so I cannot simply create it myself, but I can duplicate it. I'm just going to copy this. Okay? Now the server picks its own randomness, sends a reply, and computes the key. And now I'm going to make a state reveal on the client, which is fine. I'm not going to test the client. I'm not going to deliver I'm not going to test this client session. Okay. I make a corrupt to get the long-term secret. And now I again have all the information I need to compute the key in this session here, right? I got the long-term secret. I got the randomness, which has been used to create this message. And I got the incoming message. So I can compute the key, and I can, of course, test this. So contrary to the previous case, now I need another execution of the two honest parties. Just to see if you paid attention in the first half, is this session fresh? This one here? Can I test it? It must be fresh, right? Otherwise the attack wouldn't work. But why is it fresh? Most likely, right? I mean, there's some chance that the randomness, that the server picks the randoms and sends the same message, but it's very unlikely. Any decent protocol wouldn't have this. Plus, you would violate this 3 session identifiers, have the same this on the same honest parties. Okay, so this session, if you define the session identifier, and this is what you would do as the transcript, then this session is fresh. I can test it. Okay, this is just the link back to the model. Okay, interestingly, this attack keeps on appearing in different papers. I took the kind of this formal description from a paper by Boyd and Gonzalez Nieto. It is actually already in the BPR paper, if you look closely. It's not written that formally, but it's in there. There's a section saying, oh, okay, by the way, 2 move protocols cannot achieve that. Okay, now this is the situation, right? If you distinguish the protocol according to implicitly authenticated cases and explicitly authenticated cases, like sending a signature, and the model according to, you can do state reveals, or you cannot. Sorry, you cannot, or you can. Then the situation is, we've just seen that if I have no session state reveal, I can still mount the attack on implicitly authenticated. That was the first case. If I have explicitly authenticated schemes, but I do have session state reveals, then I can also mount the attack. naturally it follows if the adversary doesn't have state reveal and you can break any protocol, of course this means also that you can break any protocol with session state reveals, right? Just don't use it for the attack. Now the interesting thing is on the fourth square, there are examples where you can achieve this. I'm not going to talk about this protocol, but there are cases that you can really achieve forward secrecy in such cases. Okay, so if you ever design a two-move protocol, don't give up on forward secrecy. Could be that you are in this good case. Okay. And now back to weak perfect forward secrecy. This is something, a notion which Hugo defined in his HMQV paper. And again, yesterday you made fun of people calling it unknown key share attack instead of identity misbinding. The combination of weak and perfect is really, you need to wrap your head around that, right? So we all sometimes make maybe bad choices for names of properties. Oh, it's not? Are you saying this was invented afterwards?
I think I use weak PFS.
Weak.
PFS is the
Forward secrecy. Okay, I see that.
Look, I have to use UKS, I have to use KCI, I have to use Forward-Secrecy. All of these things are completely stupid names.
You just wanted to.
You know, I have to use my last one.
We cannot think of it for somebody.
Okay, so again, interestingly, if you look at the BPR paper from 2000, they already have this idea in there. Pretty much the same definition. They didn't call it weak PFS, but they already had, again, a section on that this is what you can still achieve. And the notion is basically saying sessions in which the adversary did not tamper with the communication, they should still be considered fresh, even in two-move schemes. And these concern sessions before and after the corruption. Right? So even if you, this is coming back to Yehuda's question, so even if you corrupt the party and then you have the party run an honest protocol execution, you should not be able to get hold of that session key. Okay, right, this is the place where you corrupt, and you should still not get it. What's that? Even if you have? Even if you have state reveals. That may be different. Yeah, but then you can attest the session, right? If you have corrupted the long term and you do a state reveal, the test is out of question for that one. Okay, so this is the interpretation. So you have honest executions before, they remain secure even after the corrupt. We have no idea, and this is also true if this session would actually happen here, right? Even after the corrupt, if it's an execution between two honest parties, it's still fine. If you don't have a partner here, this may be insecure because maybe the adversary is sitting here and just talking to this guy. And future sessions where the adversary is involved may be insecure. Now, if you go through the different notions, and again, if you look at the BPR paper, they also extended the notion of forward secrecy. And very often in literature today, this is kind of neglected. Right? People do not use this notion of forward secrecy, but a relaxed version of that notion. Most of the protocols actually achieve the extended version as well. Okay, and the extension in the BPR model was the following. They said every session which has been good before, the corrupt needs to be still secure. Afterwards, we don't have any guarantee anymore. But if we look at future sessions, and we know that they are run through the between honest parties, and in the model they just say if they are run through the eCK oracle, right? The eCK said two parties communicate. Here's the transcript. So they said those sessions should still be considered to be secure. And this is the part which is often nowadays neglected or ignored. But in the original BPR model, it's still in there.
And it's not implied by the original definition?
Uh,
Because if the
You're so predictable. Give me 2 slides.
I'm looking ahead.
Yes. Okay, so here you have different notions. You have weak PFS or weak forward secrecy. This is what guarantees you. This is the regular notion of forward secrecy, which you find in most of the papers today. Saying forward secrecy is good, past sessions are secure. I mean, if the adversary tampers, if it's active or if it's passive, they're both good. Future sessions, I don't have any guarantee. Not even if it's between two honest parties. Okay, now strictly speaking, this means this does not necessarily imply this. Right, because they're incomparable. I mean, it's clear that you get some stronger security guarantees here, but you have some weaker security guarantees here. Okay? Now, if you look at this BPR extended version of forward secrecy, you say if it's between honest parties, then it's secure anymore. And now you see you have the implication this way. Say it again? Oh, yeah, sure. This also holds. Absolutely. The conjunction in what sense? Oh, if you have WFS and FS. I would be very surprised. We'll get back to that maybe because I have one of the teaser for the break, next break, exactly about this question related to that. But we'll probably start diving into zero round trip time. Yeah.
Why do we care about state reveals?
Why do we care about state reveals? Because of bad pseudorandom generators, because of leakage through side channels, things like this, right? Maybe you leak some information about your randomness. The intuition is, right, the stronger the model, the better the security guarantees. But protecting against state reveals is tough, right? Yeah, I mean, could happen potentially, right? That you lose the control over your computer. A virus reads out your memory, whatever. Again, it is a nice feature, and ideally you want to have it, but it also makes it harder to design the protocol. Any other question about forward secrecy? Okay, so the next part, the first few minutes of the next part, are about a property which has emerged in the past 3-4 years, and it has also had some impact on the TLS 1.3 design because people really wanted to have this property. This property is called zero round trip time. And it's about latency caused by the fact that you need to send a couple of messages back and forth between client and server before you can actually derive the key. So here's the overall idea of zero round trip time. So this is a regular connection between the client and the server. You pick your favorite key exchange protocol and your favorite channel protocol, and you just run it there. Now, very often it happens that later the client reconnects to the server. So now you may use something like resumption, like you have a pre-shared key, but maybe you don't have this or you don't want to use this, and so on. So zero round trip time now tells you the client starts the key exchange protocol, the first message. And surprisingly, it will immediately deliver data. Okay, it doesn't wait for the server to respond. It will send its data encrypted, authenticated, anyway secured to the server. The question is, how can we do this? We're going to use something which is a weaker session key, if you like. And the weaker session key is computed from the client's contribution here and what's called a semi-static server key. Semi-static because the key is typically available for time span of anything between 3 seconds and half a day. I don't know. Around this time, right? It's not like a long-term key which you use over a month. It's not like an ephemeral key which you use in one single session. It is used in a couple of sessions, but not too many. In this sense, it's semi-static. Now the question is, where does the semi-static key come from? And here use the fact that you have talked to the server before. So you just include this semi-static key here in the communication. The server will just send the semi-static key. You as a client, you store it. Now you reconnect. You compute already this weaker session key here from this semi-static key and your contribution. And you start sending data. And then both parties can continue the key exchange protocol and then switch to the stronger session key again, right? So this was not invented by TLS, but Google was the first company to use that in the browser. The reason why Google was using this, apparently, was that very often they don't want to have the latency through the round trip time. So every time you could reconnect to your Google server, and you do that quite often, you didn't want to exchange too many messages. But if you reconnect, you can just start sending data immediately. Now, as a human being or as a client, this may save you a few milliseconds on your connection, but if you think in terms of Google, it saves them a lot of time and work, right? Because they get the data here immediately, and then later can continue the key exchange. Okay, so they put it into a protocol called QUIC. QUIC stands for Quick UDP Internet Connection. It was one of the products, basically, someone from Google here? No. Basically, Google said, oh, we need to have a faster protocol. Here it is. Use it or go away. So this is now the case where the semi-static server key has already been transferred, and it's of course not just a key, it carries a certificate and so on. And the client has, from a previous connection, right, has obtained this public key, and the server still holds the secret key. Yes. Well, from many previous connections, right? Because let's say the lifetime of the semi-static key is a day, and then you have, I don't know how many connections Google has, and it would use. Yeah, I mean, Google has all these orbits, right? And they have virtual machines, so they're not going to use this everywhere in the world. But let's say in a bigger server orbit, they would use the same key. Ah, you're asking me about the design, why Google picked this design? We'll get back to that. TLS then essentially switched from public keys away, losing something like Forward-Secrecy. Anyway, so this is the setting, right? You already have the public key of the server from the previous connection. And now you're going to connect immediately again. And here's what you do. You pick your ephemeral key, this one called E for ephemeral, and you compute G to the E. And then you can compute the Diffie-Hellman key, right? This is G to the E times S, of course, just in a different kind of notation. So this gives you your first key, and then you send your G to the E to the server. They send some more stuff, you can imagine, but cryptographically, this is what's happening.
Is semi-static key global to all clients? It's not just for...
Yes, it's global.
That's what I want to
Yeah, probably. You don't want to store too many keys for each client. Yeah, it's true, true. Question is why TLS does this. Oh, we're going to get to that. Yeah, it is related to that. Yeah, absolutely. Okay. And now the client already holds the key, the shared key, between the server. So it can immediately use this key to deliver data. So now the server can compute the key as well, right? Just computing G to the E to the S, which is the same Diffie-Hellman key. So it can actually decrypt data starting now. And now it will continue the key exchange protocol and compute its ephemeral key as well and send this key. Now, there's some kind of authentication here because now what you do is you encrypt and especially authenticate your ephemeral key under the first key. If you think about this, it's like, you know that this key belongs to the server, so the server is the only party, this is now informal, the server is the only party which can compute the Diffie-Hellman key. And then the server is also the only party which can send an authenticated message here. So this is how you know that this G to the T comes really from the server. Right? Very informal argument, but that's the point. And now they can conclude the full key exchange and compute G to the ET, which is ephemeral Diffie-Hellman, like we had it in TLS before, and it's authenticated through this key 1 from the server side. There's no client authentication. And then they can switch to stronger keys here. Stronger in the sense now this key is used in several executions and mixed with the ephemeral. This is a purely ephemeral Diffie-Hellman key. Okay, now I'm going to talk about the problems with this after the break, but for the break, I would like to come back to this question. Forward secrecy. We said that forward secrecy doesn't give you any security guarantees about future session. The extended version does. Try to think during the break of a protocol which is secure here, which is insecure here but secure here. Right? This implication holds, of course. So basically try to separate the two.